So we want to talk about drawing the Bode plot. So when I covered this in class, I started out by saying we're just going to draw a Bode plot of a single pole or a single zero. And I explained that the reason that I was doing that is because if you have a transfer function that has more than one pole or zero, because of the way the Bode plot is drawn, like specifically because it has a logarithmic axis and it does things in decibels, it means that you can simply add the individual contributions from each pole and zero to get the combined Bode plot. And I'll show you what that means. Okay. I'll show you what that means. But basically, let's go back to drawing only one pole or one zero. Okay. So in the notes, I explained why these plots are the way that they are. Today, I am just going to explain the rules for how to draw them without explaining why. So both of the Bode plots are two different plots, both of which have an x-axis, which is frequency. QUENCY in radians per second. And it is a logarithmic plot. So, for instance, it will go up in orders of magnitude each decade. And I'll go over what that means too.
Okay.
All right. So let's say you have a transfer function g of s that's like 1 over s plus a. And this a can be any value. And so we're looking at just a singular pole.
Okay.
Right? So that's the definition of a singular pole transfer function. And but for this example, let's just pretend, to make this concrete, let's pretend that we have, for instance, s plus 4. Okay. So this value here is what we call the break point. Not to be confused with a break out or break in point, which is for the root locus. Those are different things. This is called a break point, and it tells us a particular vertical line that we're going to be interested in. Okay. So what I'm going to do is I'm going to find that break point on my frequency axis. And so because this is a logarithmic plot, what I need to do to find out where that is between these 2 points is realize that 10 to the 0 is a value 1, 10 to the 1 is 10. And so in between here, we're going to count from 1 by 1s to 10. So I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And so just as another example, if we were to do the next decade, I'm starting here at 10 to the 1, which is 10, and 10 to the 2, which is 100. So I'm going to count by 10s to 100.
That makes sense.
So it'd be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay. So that's how you do your log plot. Now, I've drawn them equally spaced. On a true log plot, the ticks are not equally spaced, but the logic I just covered is the same. Okay, so let's find our break point. So our break point is at 4. So I've got 1, 2, 3, 4. Okay, I'm going to draw a vertical line at that spot on both of these plots. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that was terrible. That's okay. So this is my break point line. And it'll be important for drawing both of these plots. Now, I did not label these. That's bad. This is magnitude in decibels, and this is phase in degrees.
In phase and degrees.
Another way you can sometimes see this written is like these are just different notations for the same thing. Okay. So the magnitude plot for a single pole is going to have the same basic shape. It's just going to be shifted up and down or left to right. Okay. The same basic shape is always going to be that it starts out flat, and then at the break point, it will start going down at minus 20 decibels per decade.
About in class that's a constant. It's going to always do that for a single
pole.
A single pole. Okay.
Yep.
That makes sense.
So the break point tells us where it starts to slope downward.
Okay.
So it essentially shifts left to right. The low frequency asymptote shifts it up and down. And I'll explain what that means in a second.
Okay, yeah.
Okay. So the low frequency asymptote you can think about as like a horizontal line that tells you how high this flat section on the left side of the graph needs to be.
Okay, how flat, as in like the slope of that flat line?
No, it's where is it?
Oh, where exactly it's gonna be?
Right. It's a horizontal line. It is flat, but how high up is it?
Okay, that makes sense.
That's your low frequency asymptote.
Okay.
So I say low frequency because it's the part where the frequency is legitimately low.
Okay.
Right? It's the left side of your frequency axis.
Okay.
And to find it, what we do is we take our transfer function and you plug in j omega for s, where omega equals 0.
Omega equals 0. Okay.
So you're plugging in 0 for s. Okay. Then you need to find the magnitude. So S is always a complex number, right? It's somewhere on the real plane. What we've plugged in is a purely real or a purely imaginary input that is of 0 frequency. And what we got out is a purely real value. So if I, for instance, were to plot this output on the real axis, I would have a value of 1/4 on the real axis. And so you can think about now the magnitude of this vector and the angle that this vector makes with the real axis. So the magnitude is simply 0.25.
Okay. Because of that. Now,
Let's go back. Let's go back to the polar form of a complex number, because that's a different way of thinking about it if you don't want to think about drawing it on the real imaginary axis. A complex number S is equal to sigma plus j omega, where j is the imaginary number, right?
J is imaginary, makes sense.
And we call sigma the real component, and we call omega the imaginary component, right? This is what we call a rectangular form of a complex number. The polar form of this complex number is instead saying that there is some magnitude and some angle, where the magnitude m is the square root of sigma squared plus omega squared. And the angle is, if you were to draw this as a vector on the real imaginary plane, where you have some sigma and some omega, the angle is the angle between the real axis and that vector that points to that complex number.
That makes sense.
Okay? So that's exactly what we're not exactly what we're plotting here, but we're plotting an angle and a magnitude. The only thing is, this is what I think of as like real number magnitude, whereas this is expressed in decibels. Okay? So if I want to take this m and express it in decibels, I need to know that decibels is equal to 20 log m. Okay? All right, so if this is a complex number and there's no imaginary part, then the magnitude is simply just that real value.
Yeah.
Okay? However, we need to express it in decibels in order to find out where to put this thing.
So that's when you put it into...
Yeah. So I say, okay, the magnitude in decibels is equal to 20 log 0.25. And that sets the height of this flat portion.
And that's where that would be. That makes sense.
Okay?
Yeah, that makes sense.
Okay.
And then if that did have a imaginary component, well, so with the exam, for the exam, it's just gonna be like this.
No. By definition, it won't, because you plugged in 0 for omega.
That makes sense. Okay. So then
because it's
the
low.
Imaginary component would be 0 because it's low frequency. That makes sense.
Yes.
Okay.
So this will always give you a real number.
Mm-hmm.
In which case, the magnitude in decibels is you could, in fact, for a single pole, you could say that this low frequency asymptote is 20 log of 1 over A.
Okay. 20 log over 1 over A. Okay.
Right?
That makes sense.
Because you're always plugging in 0 for S.
That makes sense.
Okay?
Mm-hmm.
So, to draw the magnitude plot, you need to know the breakpoint to set that vertical point, and you need to know the low frequency asymptote that sets the height.
Okay.
And then that's your magnitude plot.
That makes sense.
Now, the frequency plot is actually even easier. The phase plot. I said frequency.
So for the magnitude plot, so I can understand, you would find the breakpoint first, which is going to be the vertical line based off of the single pole, or it's going to be a single pole.
Single pole.
And then you would find the low frequency asymptote, which would be the horizontal line, and then you would make sure that you convert the M value, the magnitude, into decibels, so it's on the. That makes sense. Okay.
Wonderful.
Thank you.
Very well said.
You can see asymptote after. That makes sense. How do you get that? Okay.
Okay. Now the phase plot is always going to look. This is going to be a really terrible drawing, but it's always going to look something like this.
Okay.
There's always going to be a flat section for a single pole, a flat section, and in fact, it's going to be a flat section at 0 degrees and a flat section at minus 90 degrees. So it's going to be something like this
Flat line.
and this, and in between those, it's going to have a roughly constant slope.
Okay.
Okay? The question is, where are these points?
Okay.
Okay? So let's back up again and find those before we draw this in.
That makes sense.
Okay? So what we do is we find the break point, which we already did. This is A, the break point. And I go 10 ticks to the right, or a decade to the right.
Okay.
And I'm going to mark that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to mark that with a vertical line. And I go 10 ticks to the left, or a decade to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I mark that. Okay, so now I have 3 vertical lines.
Okay.
To the left of the furthest line,
That's where
I'm at 0. To the right of the furthest line, I'm at minus 90.
Okay.
And in between, I have a nearly constant slope.
Okay.
That's it.
And that slope is gonna also be that same constant?
No, this slope is going to be minus 45 degrees per decade.
And that's a constant that will always have for a single
pole.
Okay.
Yep. And you can convince yourself of that, right? Because you know that you're going down by 90 degrees over 2 decades.
That makes sense.
Right?
Yeah, that makes sense. That makes sense. Thank you. Can you see a picture of that by chance?
Yeah, sure. I'm probably going to post this video, but yeah.
Okay, thank you. That makes sense. And now, for the exam,
I still have a lot more to do.
Okay.
We need to talk about a 0, and then we need to talk about adding.
Okay.
Okay?
Yes,
Is
ma'am.
that okay?
Yeah,
Okay.
for sure.
Okay. So a 0 is extremely, extremely similar.
Okay.
It's just that instead of going down, it goes up.
Okay.
Okay, so for a 0, the placement of everything is the exact same process, but instead of hitting the break point and going down by minus 20 decibels per decade, it'll go up by 20 decibels per decade.
So in the opposite direction. Okay,
yes.
That makes sense.
And then the phase, instead of going down by 90 degrees, it will go up 90 degrees.
Okay.
Exact same process. Everything else is the same.
Okay.
Just opposite directions.
And now, okay. That makes sense.
So now, let's talk about handling multiple poles at the same time.
Yeah.
Okay. So let's say, we've already drawn the Bode plot for 1 over s plus 4 in black. Let's choose a brighter color. And let's say instead of this, I said, I want you to draw me the Bode plot where I add s plus 10. Okay, so what I need to do is I draw the Bode plot for this, and then I draw the Bode plot for this separately, and then I will combine them together. So, but I do it on the same plot. I just do them as 2 different curves. Okay. So if I have g of s equals 1 over s plus 10, where is my breakpoint?
It's going to be at 10.
At 10. Beautiful. Right there. Yep. So I'm going to draw my breakpoint line. And then I need to find my low frequency asymptote, which is going to be what?
If you put 0 there, it's going to be 1/10, so 0.1.
Yes, but
then put it into decibels, you're right.
Yes.
That makes sense.
So this is going to be
2.
I think it's 20
log times
1/10.
1/10. Okay.
20 log of 1/10.
Of 1/10. Okay.
1/10. Yep. Okay. So now I have my low frequency asymptote and my breakpoint, and I can draw my flat line up to my breakpoint, and then my low frequency asymptote.
That makes sense.
So notice that these 2 lines have the same slope. One just starts later.
That makes sense.
Okay, and then I usually like to label this minus 20 decibels per decade.
Minus 20 decibels per decade, and the other one is, it's going to be the 45 degrees per decade for the
this
phase.
one? Yeah.
Okay, thank you.
Yeah, so now I can do this one too. I find my breakpoint at 10.
Then you go 10 to
10
the right,
up.
10 to the left.
Yep, so it'd be 10 to the 2 and then 10 to the 0.
It actually is a lot simpler than I thought it was.
It is, yeah. And then I'm 0 until I get to this guy. I'm minus 90 until I get to this guy. And in between, I'm something like this.
Okay.
With the same slope.
Okay.
Now I need to add them. Okay?
Yeah.
So when I add them, I want to look for regions of constant slope. So what that means, let's look at the magnitude plot. For the magnitude plot, when I'm in this section, both plots have constant slope.
Okay.
Right? They both have a constant slope of 0.
Yeah.
When I'm in this region, they both have a constant slope. One is a constant minus 20 decibels per decade. The other is a constant 0.
Okay.
And then the last section is here, where they both have a minus 20 decibels per decade. Okay. So I'm going to analyze each of these sections separately. So I usually want to go left to right.
Okay.
So when I'm going left to right, I just need to add these 2 values together to find out where is the flat line of my resultant.
Okay.
So let me grab a different color here. Okay. So I would need to say, okay, what is 20 log of 1/10 plus 20 log of 1/4? That value is where I put my resultant flat line.
Okay, so it wouldn't. Okay.
Because both of those plots don't change value in that section. Right? One is constantly at 20 log 1/4. The other one is constantly at 20 log 1/10. So you add them together and they remain a flat line in that section.
Okay.
Okay?
Okay, yeah.
All right. Then, afterwards, within this section, one value stays the same, and the other one starts decreasing at minus 20 decibels per second.
Yeah.
Or decibels per decade. And so within this region, the resultant also decreases at 20 decibels per decade.
So for that one, that one, there wouldn't be, like you have to add. You would just assume that it's the same rate of, okay.
Yeah, because, and then in the second region, they are both decreasing by 20 decibels per decade. So now the resultant is decreasing by 40 decibels per decade.
Because then you would add, because they're the same slope.
They're just both losing 20 decibels per decade.
Okay, so
overall, the addition of the two values is losing 40 decibels per decade.
Okay, that makes sense. So just so I understand, because these two are the same slope, you can combine these to find out what this value is here.
It's specifically because they have a slope of 0.
So because they both have a slope of 0, you can.
Yes.
Because these both don't have the same slope. One is 0, one is negative 20 decibels per decade. You can't combine those ones. You just keep the same constant of the slope as at the break point, and then because these are the same slopes, you would then combine. So is it like is it like terms essentially? Like you add like terms, or like I'm trying to like conceptualize it for. Sorry.
You can come on in, Jerry, and listen.
For like a different question, right? Like if first you did a different question, would I follow that same point of like where I combine these two because they're both 0, and then combine these two because they're also the same slope, I guess, or the constant slope, but then I would just use what the what the lowest number is then in that break point in between.
So think about it this way. The resultant slope will always be the addition of the two slopes that go into it.
Oh, so this one you essentially are you do combine them, but because it's 0, end up being the same. Okay, that makes sense. Okay. That makes sense. Sorry.
Okay, cool.
I get it now.
Okay, so this one is in this section I'm minus 20 decibels per decade, and in this section I'm minus 40 decibels per decade. Okay?
And that's gonna be a consistent I guess procedure if there's poles, but if there's zeros in a pole, it's probably gonna be different, or
you're still going to start out combining the constant section, because remember a 0 goes like this, but it still has that same flat section to begin with. So you're still going to add values to find out where your resultant starts in the flat region. And then here, you're going to go in the opposite slope. So instead of like adding them, you'll subtract them.
So say that there was a part here as well. It would be...
So if this was minus 20 decibels per decade, and this was plus 20 decibels per decade, your resultant would have 0 decibels per decade.
Okay, yeah, that makes sense. Okay, I was trying to make sure that that's what that procedure would be. But then, like, say that it has two poles, but one 0, that obviously would be different, since it wouldn't be a flat line, and then you have to like add those in to figure out what they'll look. Okay,
yeah.
That makes sense.
So it would add in as a positive, whereas these are added as a negative.
That makes sense.
Yeah. Okay. Very good. Okay. For the phase, you want to do the same thing. You want to look for regions of constant slope. So I've got a region here. This is different because one of them starts changing. This is different because they're both changing all the way up until here. And then here is another one. And
that's the last one.
They're both at minus 90. Okay. So here, I need to add a value 0 and a value 0, so I get a 0. So my resultant is here. Here, one of them is decreasing at minus 45 decibels per decade. The other one is 0.
So you keep that flat. You keep that.
Yep.
That makes sense. And then because they're both, you would essentially multiply that by 2, because you're gonna add them both. Okay.
So now within this section, I'm going down by -90 decibel or 90 degrees per decade. And then here I flatten out again a little bit. And in this region, they're both minus 90.
They're consistent.
So you're down at minus 180 degrees.
Then you go pretty much a flat line.
Flat line.
That makes sense. Okay.
And
then,
I usually like to label these sections as like minus 45 degrees per decade, minus 90 degrees per decade, minus 45 degrees per decade.
That makes sense. And that's it.
That's it.
That situation.
That
makes sense.
Combining them.
Okay, that makes sense. So just so I understand, we talked about, so what you would do for everyone you plot, you would start with like a single one. So a single zero or a single pole to start off with, and then you combine them all.
Yes.
Make sure that you find the breakpoint, which is pretty simple to find.
Yep.
From the breakpoint, you can figure out where it's going to change here, and that's going to be your A value, essentially. The constants for the magnitude and phase are always going to be constant, except when you combined it, it's just going to change based off of that.
The slopes, you mean? Yeah.
The slopes, yep. And then making sure that for the M value we have, that we change that into
decibels.
The decibels. Besides that, that's really it.
Yep. And then don't do the mistake I did in class. This is log base 10.
Okay.
Not ln.
Nice.
Yeah, MATLAB does that automatically, right?
That's why I goofed, is because I was using MATLAB and I forgot.
That error took me like an hour to figure out one time when I was working with it.
Yep.
I think it was for dynamics too.
Yep.
Why is this not matching up?
I don't know why they do that, other than maybe there was already a built-in function for the ln.
Yeah.
That makes sense.
I don't know. Okay, I'm going to stop.